Okay, this is our last day. I apologize in advance for having new material on the last day of class, but we had a little unscheduled problems. And this topic is really important. Every computer scientist needs to know the internal workings of floating point representation. All right, so here we go, floating point representation. So we know how integers are stored, right? Using 2's complement binary representation. Remember that? The first bit is the sign bit, and we can convert from, decimal to binary, negative numbers. The question now becomes how do floating point numbers work, where you have a fractional part? Well, it's really very similar to the way we do it in decimal. In fact, it's not really not that difficult to understand. Let's take a look at figure 3.28. This is an example of a number 101.011. So now, instead of calling it the decimal point, we call it the what? It is a floating point number, but why do we call it a decimal point? Because it's base what?
Base 10.
Base 10. But now what base are we in?
A binary point.
So it's a binary point. We're in base 2. So we call this the binary point. All right? So what is 101.011? Well, think about it for a minute. If we were in decimal, the first digit to the left of the decimal point is which place? To the left of the decimal point is which place? The ones and then the what? Tens and then the what? Hundreds and then the thousands, right? And then to the right of the decimal point, it's what? The what?
1/10.
The 1/10th place, and then the 1/100ths and the 1/1000ths. So with binary, it's to the left of the binary point, it's the 1s, the 2s, the 4s, the 8s. But to the right, it's the what? It's the 1/2 place, 1/4, 1/8, 1/16. So that's illustrated here in figure 3.28. You've got the halves place, the 4th place, if there was one more, it'd be the 16th, the 32nd point, the 1/64th point. And so what is this? So how do you convert from binary to decimal? Well, to the left of the binary point, it's 101, so that's 5, right? And to the right, we have what? We have nothing in the halves place, so we have a 4th plus an 8th. And so that's 5.375. And here is the polynomial representation. In decimal, the number 506.721, that's 5 times 10 squared, plus 0 times 10 to the 1, plus 6 times 10 to the 0, etc., etc., etc. And in the binary, it's the same thing, but we use times 2 to the instead of times 10 to the. Now, it's easy to go from binary to decimal. But we have to learn a few little techniques, algorithms, to go from decimal to binary. So let's do 6.5859375. Okay, so as an example for going from decimal to binary, let's try to convert this. All right? So here's how it works. First of all, we do this in 2 parts. We know how to go from how the integer part works, right? So 6 in decimal is what in binary?
110.
110. By the way, if it were a really big number, how would you do it? You knew this because this is the 0's place, the 1's, no, sorry, the 1's place, the 2's, the 4, and 2 plus 4 is 6, and no 1's place. But if it were a real big one, what would you do? You successfully divide by 2, and you write down the remainder. And the remainder is either going to be 0 or 1. Remember how that worked? Now, what's interesting is, how do you do this part? To the left of the binary point, you successively divide by 2. To the right of the binary point, you successively multiply by 2. And instead of writing down the remainder, you write down the number to the left of the binary point, or the decimal point. Okay, so here's what you do. We start off, so watch how this works. We start off with 0.5859375. 5859375. what is 0.5859375 times 2? So 1 point, right? And now what we do, and so we put the number to the left of the decimal point over here. But now what happens if we multiply 0.171875 times 2? You have that one?
That is 0.34375.
And that's 0 point. And what is 0.34375 times 2? Okay, so say it again.
0.6875.
And then 0.6875 times 2.
1.375.
Ooh, now 0.375 times 2. 0.75, right? The leading, all right? And then 0.75 times 2 is what? And 0.5 times 2 is what?
1.0.
Yeah, 1.0. And 0 times is what?
0.
0, 0, 0, 0, 0. So what is this number? It's 110 point, so here's the 6 point. Now, is it 1001011 or is it 1101001? Yeah, it is the first. How could? Yeah, because we have trailing zeros after that don't change the value. So it's 1001011. 1001011. Right? So that's shown here in figure 3.30. Does everybody see how that works? So that's the first big deal, but it's just what you would expect, just how you would expect it. Now, here's the thing. So we all know scientific notation, right? So how would this be written in scientific notation? Isn't there a convention that the decimal point always belongs like after the first non-zero digit? And then you multiply it times 10 to the whatever, okay? So the thing that we do with this is we normalize it, all right? So instead of having we move this binary point to the left, whoosh, whoosh, 2 places to here. But then, so what is the number written in binary scientific notation? It's 1.101001011. But now what did we do? Would this be times 2 to the 2 or times 2 to the negative 2? We're making this smaller, so it'd be times 2 to the 2. So as shown on the slide. Does everybody see how that works? Yeah, question?
What about, I have a question.
Ooh, that is a really good question. As a matter of fact, let's do one. I paid her to say that. You know how the magician always has a plant in the audience? She's my plant. All right, so check this out. Let's convert 0.2. Let's convert 0.2. Now watch this. So what's 0.2 times 2? 0.4. Now watch this. 0.8, is that right? And what's the next one? 1.6, and what's the next one? 1.2, and what's the next one? 0.4, and what's the next one? 0.8, and what's the next one? 1.6, and obviously what's going to happen? Once we got to here, that was the same as here, right? So how is 0.2 stored in binary? It's point what? 001100, so it's point 001100110011, etc. So here it is, figure 331, which is an interesting phenomenon. Do you realize that you cannot store 0.2 exactly in binary? Because in binary, we know that to store values, to store numeric values, we have a certain finite number of bits to store them in, right? Memory is not infinitely long. So anytime you have, if you write a C program that says, you know, X x is, a double or something, you say x gets 0.2. If you do arithmetic on that, it's not exactly 0.2. If you multiply 0.2 times 5, you might not get exactly 1.0. You might not get exactly 1.0 because 0.2 there's going to be a round-off error, and so if there's going to be an error, it might not be exactly 1.0. So what do we have to do? We're going to have to be able to store this. We're going to have a round-off. We're going to have to round it off to store for finding, and we'll see how to do that. There's a specific algorithm to do that. Getting back to 6, it's that number that we had, 6.5859375. It's 1.101. What are we going to have to store in order to store a floating point number? What are we going to have to keep track of to store a floating point number in binary scientific notation? Yeah, we're going to have to store this string of bits, which is the significand, but then we're also going to have to store what? The exponent. And we're also going to have to store what? Whether it's what or what? Positive or negative. So we're also going to have a sign bit. Is everybody clear? So here in figure 3.32 is the layout of a floating point value inside the computer. The first bit is reserved for the sign of the entire number, and the exponent is how we store this integer exponent value, and this exponent could be negative, but that's stored within the exponent field. And then the significand are the bits that actually, are that represent the magnitude of the quantity, right? And each one of those and depending on the system, these fields, the sign bit is always just one bit, but you just pre-allocate so many for the exponent and so many for the significand, and yeah, so that's how it's done. Now, look, you guys, here's another thing. If we always normalize our numbers so that the decimal point is always after the leading 1, that means that we know that this will always be 1, right? And furthermore, does everybody see that the more bits we allocate for the significand, the more precise the number is? So do you see something, a really clever thing that we can do to squeeze a little bit more precision out of the significand? Yeah, just don't store this first one when we go to store it. And that's called the hidden bit, so we're going to hide it. So here, that's the hidden bit. With the hidden bit, what happens is, in normalized scientific notation, it always has 1 to the left of the binary point, so don't store it. And that means that we have an extra bit of precision in the significand. But now, of course, what has to happen is the floating point unit that does the computation, when it gets something from storage, it has to insert that 1 in there and then do the computation. And then after it's done the computation, when it wants to store it back into memory, it removes the hidden bit and stores it that way. Does everybody see the concept of the hidden bit? Yeah. But, oh, you mean the number 0?
We're trying to store 0, yeah.
Oh, that is a really good question. That's my second plant. The question is, how are we going to store 0? Because 0 doesn't have a leading 1. So that's going to be a special value. We're going to have to treat that special case. In order to do this, we're going to need a special case. And that's one of several special cases that we're going to incorporate in the signed floating point representation. Yeah, that's a good. So we're going to hold that thought for a few minutes, and we'll get right to it. But before we do that, let's come back here to the format here in figure 3.32 and think about how are we going to store the exponent. Now this exponent is an integer, right? Are you with me? The exponent itself is an integer. And we know how to store positive and negative integers, right? So what do you think would be a good way to store, like if it were some number times 2 to the -5? What would you think would be a good way to store that -5? What would you think would be a natural, the first thing that would come to your mind? How would you store that? Yeah, just a signed integer and use 2's complement binary representation, right? You would think on first blush that that's how you would do it. But that's not how it's done. We have and I can't explain it right now, but we'll explain it in a few more minutes. We will see why it's not done that way. And there's a good practical reason for why it's not done that way. But take it on faith now that it's not we don't use 2's complement binary representation to store the exponent. Instead, we use what is called an excess representation. Figure 3.33 is an example of what is called excess 3 representation, and it's contrasted with the 2's complement representation. So if you look at the 2's complement representation, in 2's complement, if you have a 3-bit field, you can store the values -4, -3, -2, -1, 0, 1, 2, and 3. So the range of integers in 2's complement representation goes from -4 to 3. Are you with me on that? And furthermore, the first bit, if the first bit is a 1, then it's a what? In 2's complement representation, if the first bit is a 1, then what kind of a number is it? What kind of an integer is it? It's negative. Now, in contrast to that, the excess 3 representation has a range from -3, -2, -1, 0, 1, 2, 3, up to 4. And furthermore, look, what about the sign bit? If the sign bit is 1, the number is what? Positive. But that's the way it is. And you see that, I mean, it's possible. I mean, we just assign the negative and positive values this way instead of the other way. So let's do some examples. Excess 3 with 3 bits. Now watch this. So here's the question. How do you store 2? So here's going to be the recipe. Here's going to be the algorithm for converting. So how to store 2? How to store 2? What you do, and this is excess 3. Are you with me? So what you do is you take 2 plus 3, and that's what? 2 plus 3 equals 5. Right? That, and how would 5 be stored unsigned? 1, 0, 1. Well, look at the chart. Where is 2? It's right here. And how is it stored in excess 3? 1, 0, 1. Does everybody see how that algorithm works? Are we good? How to store -2? So what do? You take what? -2 plus what?
3.
Plus the excess. So -2 plus 3. And what is that?
1.
That's 1. And how would you store 1 using 3 bits unsigned? 0, 0, 1. And look, -2 on the chart, 0, 0, 1. Now, does everybody see how that works? Now, of course, in a real system, it's not just excess 3. A common one is excess 127. So, how to store 2? Well, how would you store 2? You would take what? 2 plus what? 127. So 2 plus 127. And what does 2 plus 127 equal? 129. And so if you convert that to binary, it's going to be what? It's going to be 1, 0, 0, 0, 0, 0, 0, 1. And you can tell this is 129 because it's 128 plus 1. And then how to store -2? Well, it's -2 plus 127 equals what? 125. And if you convert that to binary unsigned, what do you get? 0, 1, 1, 1. I think 1, 1, 0, 1. So now let's do an example with, now I have a really tiny example of how this works so that we can, with really small numbers. In the real world, the fields are a lot wider, but the concept is exactly identical. So we're going to use a running example. Running example, it's going to look like this. We're going to have 3 bits for here and 4 bits and then 1 bit here. So it's going to be 1 sign bit, 3 exponent bits, and we're going to have 4 significand bits. All right, so that's what we'll do a bunch of examples with this All right, and here's the question. How is 3.375 stored? How is 3.375 stored? Well, so we take it in parts. How is 3 stored? To the left of the, so how is this being, it's 3 in binary. 1, 1. Is everybody good? So this is 1, 1. Now what about the 0.375? Can somebody whip that out real quick? 0.375 times 2 is 0. So this is going to be 1.0 something, right? 1.011. Actually, we can tell this right away, right? Because this is the halves, this is the 1/4, and this is the 1/8. So a fourth is 0.25, and an eighth is 0.175, and then 0.1. I think that's right, yeah. And so what is this in binary scientific notation? So normalize it. So what do we get? 1 point what? 1.1011. Is everybody clear? Times 2 to the what? Times 2 to the 1, right? So now how is 1? Now this gets stored in excess representation. So 1 decimal equals what? Excess 3. Yeah, you just look at the chart.
100.
100. This is excess 3. Is everybody clear? So that's this. That's the exponent. Are you with me? And now what's the hidden bit? This one. So the significand is this part, right? So therefore, and is it positive? Is the number positive or negative? It's a positive. So what? So how is it stored? 0, and then what? 100, and then what? 1011. Now, does everybody see how that works? And it's like this. Here's the sign, here's the exponent, and there's the significand. Are we good? The question comes about how to round. If like if we had that 0.2 and we go. Now, have you guys learned that? Do you guys know this rule? It's called round to nearest ties to even. Have you ever heard of that? This is the algorithm that's used to round off when you have to approximate values in floating point representation. It's called round to nearest ties to even. Now, and here's the problem. If you round off 23.499, rounded off, that's what? To the nearest whole number is 23, right? Is everybody? And if you round off, and if it's 23.501, that's closer to 24 than it is to 23, so that's 24, right? And if it's 24.499, that's closer to 24 than it is to 25, right? And if it's 24.501, that's closer to 25 than it is to 24, so that rounds off to 25. But the question is, what happens if it's right in the middle? What happens if it is 24.5? Or 23.5 or 22.5. How do you round that off? And here's the problem. If you're doing a numerical computation where you always, when it's right in the middle, if you always round down, can you see that if you're doing a complicated mathematical computation that has lots of iterations, eventually things are going to, your results are going to drift down. But if you always round up, what will happen? Your computations might, because of this approximations, your computations the values might eventually drift up. So what do you want to do? Half the time round down, half the time round up. Do you see? So the way you can decide this, instead of, you could have a random number generator that does it randomly, which would be good, but then that's inefficient. That would take some more computation. So the rule is, round to the nearest, but then if it's tie, you go to the even. See how that works? So it's round to nearest ties to even. So what happens is, in decimal, if it's 23.5, well, the question is, do you round down to 23 or up to 24? And it's a tie, so you round up to 24. On the other hand, if it's 24.5, the question is, do you round down to 24 or up to 25? Well, 24 is even, so you round down to 24. And it's the same thing in binary. Does everybody see how this works? It's the same thing in binary. So what happens is, in binary, if it's 1011.011, well, that's closer to what? 1011, because that's not a tie. And if it's 1011.101, well, that's closer to 1100, because that's not a tie. But what if it's 1011.1? Then that's halfway in between. So which do you round it to, 1011 or 1100? Ties to what? Even, so it's 1100. Is everybody clear on this? Does everybody see how this works?
I'm a little confused.
23.501 is bigger than 23, is closer to 24 than it is to 23.
I'm sorry, I looked at that wrong.
Yeah, it's tricky. And it's especially tricky when you're doing it with ones and zeros. But it's the same concept. It's just in binary. All right, so let's do it. Let's do an example. Let's do an example where you have to do where we have to do this. So how is, we'll do it with our small example. How is negative 13.75 stored? So 13.75 decimal. We won't take the time to, I mean, you can figure out what 13 is and what 0.75 is, right? Like we did before. And 13, does anybody know? I think it's 1101. Is that right? 1.10111. 1.10111. Times 2 to the what? Times 2 to the 3. And then 3 decimal is what? Excess 3. 110 excess 3. This one is hidden. This one is hidden. And now how many bits do we have left over for the significand? We've got 10111, right? So the significand, let's write that down. The significand is 10111. Because we're going to hide this and we have this, right? But how many, in our little tiny example, how many bits do we have? We only have how many bits allocated for our significand? Only have 4. So 5 bits. Only 4 bits available. So what do we have to do? We have to round off the last one. Yeah? Is everyone, are you good? So here's the question. How do you, if there were a decimal point here, you know, if there were a decimal point there, and we were, or a binary point rather, 1011.1, and the question is, if we round this down, what would we have? We would have 1011.0, and if we round it up, what would we have? 1100.0. So this one is rounding down, and this one is doing what? Rounding up. And furthermore, it's a tie. Right? It's just as close to this as it is to this. So ties go to what? Ties to even. So which one is even? 1100. Tie. So the tie goes to 1100. The tie goes to 1100 because it is even. And 1011 is odd. And 1011 is odd. So therefore, how is it stored? Now this was a negative number, right? 1. And then for here, for the excess 3 is 110. 110. And then 1100. Now comes the special values. That 0 is a special value. And what we're going to have to do is we're going to have to rob, if the exponent field is all zeros and the significand is all zeros, that's how we're going to store 0. But now what that means is the sign bit could be either a 1 or a 0. So in this representation, there is a negative 0 and a positive 0. If the exponent field is all zeros and the significand is all zeros, then we don't have a hidden bit, you know, like we usually do. And what happens is, figure 3.35 shows the number line with 0 being the only special value. And so if you use this 3-bit exponent, 4-bit significand, there are these regions. There is a, you can store numbers anywhere from 0.13281125 to 31.0, and anything bigger than that is positive overflow, and anything between that and 0.0 is a positive underflow. Now, there are 3 more special values. First of all, infinity. What happens if you divide by, what happens if you do 5 divided by 0? What do you get? You could say it's infinity. So there's actually a way to store infinity. And infinity has the mathematical rules that if you add infinity plus 5, what do you get? You get infinity. And if you take 5 divided by 0, you get infinity. And if you take negative 5 divided by 0, you get negative infinity. But all of your computations after that are infinity rules. So that's one special value. Another special value is not a number. They're called NANDs. Have you ever had NAND come out in a printout, when you're doing floating point stuff? It happens occasionally. If you ever see, it's abbreviated NAN, called not a number. Not a, yeah, actually you're right. It does usually come out with a lowercase. And how can you get a NAN? Not by dividing by 0, but by doing something like what? How about taking the square root of a negative number? So that's not an infinity, but it's just not defined for real numbers. So that's one way to get a NAN. And here again, the rules follow not a number. If you ever add something to not a number, what do you get? Not a number. If you, yeah, so it kind of absorbs all your errors, and so in the end, oh, you know something happened along the way. If you multiply not a number with infinity, you get not a number. So there are rules like that. Here's a special value for infinity. Here is the special value for not a number. And there's one more special value. Now check this out. This is in figure 3.37. In figure 3.37, what we have is, again, this is for that small example where we have a 1-bit sign and a 3-bit exponent field. And if you look at the top figure of figure 3.37, this is the way it is, the way we've described it so far without these special denormalized numbers. And look at how the gaps are between the values represented on the real number line. You see that anywhere between 0.125 and 0.25, the adjacent values are all close together. Those are for a multiplier of 2 to the minus 3. And then the next 16 numbers are between 0.25 and 0.5. Those are the values with a multiplier of 2 to the minus 2. And then the next ones are 2 to the minus 1. And each time you go up by 1 in the exponent, they get more spread out. Well, if you notice what happens there, there's a big gap between 0 and that, you see it's kind of an unusual gap that's apparently unavoidable. Well, the special value of the special denormalized value takes this smallest exponent and it takes those values and it spreads them out, giving us a phenomenon called gradual underflow that alleviates bad things that can happen when you compute with exceedingly small values. And there's a rule, there's a rule for how to calculate these special values with using denormalized numbers. And a denormalized number has an exponent field of all zeros, and the significand is non-zero. The hidden bit is assumed to be 0 instead of 1, and if the exponent is stored in excess n for normalized numbers, it is stored in excess n minus 1 for denormalized numbers. Like in our small example, if it's stored in excess 3 for normalized numbers, it's stored in excess 2 for denormalized numbers. Now here comes the answer to the question of why use excess 3. This is in figure 338, actually. Let's take a look at the positive values. If you use excess 3, do you see that starting at 0 and then the smallest positive denormalized number and the smallest normalized number, and as we go up, what does it look like if you consider the whole thing to just be an integer? Each value is what? As you go up, as you increase, as the values increase, if you consider the whole thing, if you just merge together the sign bit and the exponent field and the significand field, if you just merge them all into one integer, do you see what order you have? They are in order. Considering, just if you consider them to be what? Just integers. And it's even, look, if you go back this way, to the negative part, it's the same thing. You start with 11100, and then you just add 1. You get the next one. So that means that the circuitry can be integer circuitry when you're comparing two floating point values. You can use integer circuitry. You don't have to extract this and shift this and put the hidden bit in and boo-boo and then figure out. You see what I'm saying? You can tell, the hardware can tell which value is greater than which other value just by using the same circuitry that it would if it were an integer. It wouldn't be, you wouldn't have that property if you used 2's complement binary representation for the exponent. Okay, so we're going to finish this lecture offline. Again, we're lecturing to an empty classroom with my trusty camera operator. Josh, thanks for pitching in. So we were talking about in figure 3.38 is the situation with floating point numbers with this tiny example that we had with 1 bit, 3 bits, and 4 bits. So 1 bit is the sign bit, 3 is the exponent, 3 bits for the exponent, and 4 bits for the significand. And in figure 3.38, the second half of figure 3.38, we see those values which are denormalized. Remember that so the denormalized numbers are the numbers with 0, 0, 0 in the exponent field. So we see here that the smallest positive normalized number is the bit pattern 0 for the sign bit, 0, 0, 1 for the exponent, and 0, 0, 0, 0 for the significand. And that's 0.25. So we see in this figure that all numbers less than 0.25 are stored denormalized. So let's do an example. The question is, how is the decimal, so here's our question. How is the decimal number negative 0.078. Negative 0.078 stored, okay? So this is the example we'll do. Okay, so now what's the first thing that we notice? We go over here to this table and we notice that 0.078 is less than what? 0.25. Do you see? So that's our first observation. 0.078 is less than 0.25. Therefore, it must be stored normalized or denormalized? Denormalized, right. Denormalized. So we have to know that. Now, what does that mean? That means that the exponent field is all what?
That's going to be all zeros?
Yeah. So the exponent field is all zeros, okay? And that means the hidden bit is what? I mean, normally the hidden bit is 1, right? But if they're denormalized, the hidden bit is what?
0.
Yeah. So this implies that the hidden bit is 0, and so we'll put parentheses here, not 1, which it would be if it were normalized. And that means that the exponent is stored excess what instead of excess what? In excess 2 instead of excess 3, okay? So those are the rules that apply for denormalized numbers. Okay, so 0, 0, 0, we know it's 0, 0, 0, right? So 0, 0, 0, excess 2 is what? Is negative 2 decimal, right? Because you subtract. Remember, you take you take 0 minus 2. It's excess 2, so it's 0 minus 2. So that means that means the exponent is negative 2. So that means that the multiplier is 2 to the negative 2. And the multiplier is 2 to the negative 2. So how do we do 0.78? So 0.078 decimal. So I'm not going to take the time to do it, but you successively multiply by 2 and keep track of the point to the digit to the left of the decimal point. And if you work that all out, that's this. That's 0.00010011 ... All right, so that's what 0.078 is. Okay, and now we have to write this. So what did we say over there? We said the multiplier is times 2 to the negative 2. So the question is, this equals what times 2 to the negative 2? You see, because we know the multiplier is 2, you know it's denormalized, so we know the multiplier is times 2 to the negative 2. So what this is what times 2 to the negative 2? Where do I shift the decimal?
Right.
Yeah, we shift it to the right 2. So this is 0.01. So this is 0.010011 ... times 2 to the negative 2. Now, does everybody, you see how we got that? Because we know with denormalized numbers that the exponent is negative 2. So this is, and sure enough, as advertised, what is this? As advertised. As advertised, what is this bit? The hidden bit is 0. How many bits do we have to store for the significand? 4, right? So which ones? Here, I actually have a. So which 4 bits do we store? We store these 4. But, of course, what do we do? 0, 1, 0, 0, but it's 1, 1, 1, 1. So we do what? Round off, right?
Right.
So these 4 bits are 0, 1, 0, 1. We said the exponent bits were what? All zeros. So that's 0, 0, 0. And furthermore, the original number was what? Negative. So that means the sign bit for the whole thing is what? 1. So there it is. Divided into these fields. Boom, boom, boom. Okay? Now, figure 3.39 shows IEEE 754 floating point. IEEE is the Institute for Electrical and Electronic Engineers. It is it's a professional society that, among many other things that it does, it promotes standardization in the electrical engineering community. And 754 is the number of the standard that they did. And this standard, by the way, this standard was very controversial in the early days. It has an interesting history, but eventually it became adopted and it became this IEEE 754 floating point standard. And this is virtually every manufacturer provides. This is the way floating point processing is done. In the early days, every computer manufacturer did their own thing. They had each manufacturer had a different way of storing floating point numbers with decimal points. And so this was a big advance in the community. Now, the only everything that we have done so far has the IEEE 754 floating point standard is exactly the same as we've described it, with all these special values, the nands, the plus and minus infinities, the 0, the way 0 stored, the denormalized numbers. All of that is part of the IEEE 754 floating point standard. The only difference is how many bits are allocated for the exponent field and for the significand. And look here in part A. In part A is how single precision is stored. Now in C, this would be a float. So if you use float, it's stored with how many bits altogether? 23 plus 8 plus 1. 24, 32. So that's a 32-bit quantity. And what happens is there's 1 bit for the sign, 8 bits for the exponent, and 23 bits for the significand. Part B shows double precision. Double precision in C is denoted double. And so it is 64 bits. And the only difference between that and single is there's more bits allocated for the exponent and more bits allocated for the significand. There's 11 bits for the exponent and 52 bits for the significand. So that's lots of precision. All right? But other than that, everything that we've done is IEEE 754 floating point. So let's do a few examples. Okay. So let's do an example with single precision, just to keep it shorter. All right? And the question is, how is negative 47.25, negative 47.25 stored in single precision? So now, so we have to do this in several parts. First we've got to do the 47, then we've got to do the 0.25. Now 47, you know what 47 is offhand binary? Probably not. Well, if you work it out, let's do, so here first, 47, you successively divide by 2 and do the remainders. But if you work it out, 47 is 101111. 101111. Binary. This one you probably should be able to do, actually. What is 0.25 decimal? What is that? That is 0. Oh, very good. You remembered. See, it's 0.01. Because this is the halves place, this is the quarters place, and this happens to just be 0.25, which is a quarter. 1. So that means in binary scientific notation, what is this number? In binary scientific notation, it is 101111.01, right? Or sorry, in binary notation, it's this. Now we've got to change it to binary scientific notation. So to normalize this, what would we do? So this equals, so we have to move the decimal place over what? 1, 2, 3, 4, 5, right? So this is 1.011101 times 2 to the what? Times 2 to the 5. So now what we have to do is we have to figure out what 5 is, how to store the 5. So 5 decimal, so how do we do that? So what we have to do is we have to figure out how 5 is stored in XS 127. So how do you do that? You do 5 plus 127 is what?
132.
132. And then 132 decimal, and 132 decimal is what in binary unsigned? Well, yeah, you'd have to divide by 2, blah, 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 blah. If you work all that stuff out, it's going to be 1000, 1000, 0100, 0100, and this is XS 127. Now, and this is 8 bits, all right, for the exponent field. And notice that, remember, with XS, the fact that we have a 1 in the sign bit means that it's positive, because it's the opposite of the way it is with 2's complement binary representation. So this is the bit pattern in XS 127 for the exponent, all right? Another thing we have to remember is that this is the what? What bit is this? This is the hidden bit, so we don't store it. So that's the hidden bit, so we don't store it. So now we're ready to write down the binary. So the binary. So first of all, the number is negative, right? So that's 1. The exponent is 1000, 1000, 0100, 0100, and then the significand is 01111010000 up for 32 bits. And if you were to write this in hexadecimal, you would take these 4, even though this is the sign bit and this is, and then these 4, and then these 4, and then these 4, and then a bunch of zeros. And so what is this in hex? Do you remember what 1100 is? Yeah, that's C. And then this is what? 0010?
That's just a 2.
That's 2, and then this is
That's
3,
3.
and this is D, and then 0000. So there it is in hex. So now let's do one more example. Let's go the other way around, okay? So let's suppose we have 3CC8, 3CC8, 0000. And so let's suppose that you have this bit pattern, and let's try to figure out what floating point number this is. So we expand this out, so 3 is what?
0011.
0011. Remember what C was we just did?
1100.
1100. Another 1100. And 8 is what?
1000.
1000. 0000. Dot, dot, dot. So now we have to just peel this off. This 0 is the what? Sign bit. And 1, 2, 3, 4, 5, 6, 7, 8. So here to here, and then from here on. So this is the sign bit. We know it's positive. So now we have to convert 011110001. So what is that? So 011110001. Okay, yeah, good point. So the first observation is there's a 0 in the sign bit, so this is going to be a negative number. But how do you get what that negative value is? Well, we have to get the positive number for this. So what is this? Is the 1, 2, 4, 8, 16, 32, 64. What is 1 plus 8 plus 16 plus 32 plus 64?
121.
That's 121. So does everybody see how we got that? That's 121. But now we're going from decimal to excess. So now what do? We subtract one. It's excess 127. So now what's 121 minus 127?
It's -6.
That's negative 6 decimal. And sure enough, as advertised, there's a 0 in the sign bit, which with excess notation is makes it negative. By the way, we are only going to write this in binary scientific notation. So therefore, what's the number? It is here. This means it's positive. Oh, and by the way, what's the hidden bit? Is a hidden bit 1 or 0? We have to know that this is a normalized number. We're not dealing with denormalized numbers. And so what's the hidden bit, 1 or 0?
It's normalized.
It's 1. So the significand is 1001000, but the hidden bit is 1. Are you with me? So therefore the number is what? 1 point. And then 1001. 1001. 00000. Are you with me on this? And then this is times 2 to the what?
To the -6.
To the -6. So it's 1.1001 times 2 to the -6.